In this video, I'm going to continue the discussion of compatible and incompatible variables. So this is part 2. So we worked out in the previous video that you can use the commutator to decide or to figure out whether or not two variables are compatible with each other. So now let's talk about a more practical reason as to why we're going to look at these two different variables and see whether or not they are compatible. Basically, how does this work? Because I keep talking about two operators. Let's say these two operators we keep calling omega and lambda, and these two operators we can operate with one first and then the other, but the first operator that operates is going to change the state, and therefore the second operator is now operating on a different state than the initial state in the problem. So let's just say we have these two operators are compatible with each other. So their commutator is equal to 0. And let's say that this operator omega has eigenvalues of omega 1, omega 2, and omega 3. The operator lambda has eigenvalues of lambda and lambda 3. So what we're setting up is there's going to be a degeneracy in the lambda. And so in the end, what I'm basically saying is that this lambda, there are 3 eigenvalues, but lambda 1 is equal to lambda 2, which is just equal to that value of lambda. So let's consider basically the first experiment, experiment number 1, where our state is some factor alpha times the state omega 3 lambda 3 plus beta times the state omega 1 lambda plus gamma times omega 2 lambda. So like I said, lambda in state 1 and state 2 right here is degenerate. So we'd get the same value of lambda if we operated with the operator capital lambda, but if we operate with the operator omega, then we would get 2 different values of it. So that's where we have our degeneracy. So if we want to say, let's measure omega 3 first, then lambda 3. Okay, so basically the probability of measuring omega 3 then lambda would be the projection of omega 3 lambda 3 on psi and then squared. So in this case what we would do is we would say well, let's take the projection omega 3 lambda 3 on psi, which is equal to alpha omega 3 lambda 3 on omega 3 lambda 3 plus beta times omega 3 lambda 3 on omega 1 lambda plus gamma omega 3 lambda 3 omega 2 lambda. So since these states are orthonormal, then this first one is equal to 1, the second one is equal to 0, the projection of the third one is also equal to 0. So in the end, what we're left with is alpha. So we've selected that omega 3 lambda 3, and that gave us a factor of alpha, so that if we square it, then what we get for our probability is alpha squared. So what if we try to do this process in reverse? What if we now try to get the probability of lambda 3 then omega 3? Well, that would be lambda 3 omega 3 projected onto psi squared. And, since omega 3 lambda 3 is orthonormal with omega 1 and lambda, omega 2 and lambda, what we would get is we would get the same answer of alpha squared. So in the end, in this case, it doesn't matter the order at which we calculate the probability. We can measure omega first, and then followed with a measurement of lambda, or we can measure lambda first, and then make a measurement of omega, and in the end we would get the exact same answer. We would be just taking a slightly different path to get there. So now let's consider experiment number 2, where now we want to measure omega 1 then lambda. So in this case, if I was to do that, so the probability of measuring omega 1 then lambda would be the same thing. I'm projecting omega 1 lambda onto psi, and then I square it. And so in this case, we would get this projection of omega 1 lambda onto psi would be alpha omega 1 lambda omega 3 lambda 3 plus beta omega 1 lambda omega 1 lambda plus gamma omega 1 lambda product with omega 2 lambda. So in this case, this first product is 0, the third product is 0, the second product is equal to 1, and so in the end, my probability is beta squared. Okay, it's pretty simple. We first selected omega 1, which eliminates the other two products, and from there we just operate and get lambda, and we get the answer of beta. But now, what if we measure lambda first, then we measure omega 1? So if we do that, basically, if we operate here with lambda on psi, selecting the other lambda, then we get the two degenerate states. We would get beta times omega 1 lambda plus gamma times omega 2 lambda, and then we would get the normalization of beta squared plus gamma squared, square root of that. So we by selecting the degenerate states, we would select both of them. It's still a superposition. We haven't decided yet have we selected omega 1 lambda or omega 2 lambda. Those two possibilities still exist, because all we've done so far is to make a measurement of lambda, selecting the eigenvalue of little lambda. And so now what we want to do, or I should say, so therefore the probability then of, okay, so now what we would want to do is we want to select omega 1. So now if we operate with omega on our measured state of lambda times psi. Now we're just going to select this first term. The other term, omega 1 and omega 2 are orthonormal. So in the end what we would get is we would get beta times beta squared plus gamma squared to the 1/2 power. And now when we find the probability, that probability of measuring lambda first, then omega 1 would be the probability of getting just lambda times my beta squared over beta squared plus gamma squared. So now this probability of just getting lambda would be beta squared plus gamma squared. So in the end, the total probability would be beta squared plus gamma squared times beta squared over this normalization. And so in the end, what we would get is beta squared again. So the good news is that with these compatible operators, that if we measure omega first, then lambda, we get the same probability of the reaction occurring if we instead measured lambda first, then omega 1. We get the same result. We would get a probability of beta squared. The only difference is the path that we took. And so you can think about this as kind of, if you think about energy levels in the atom, where this is the first state, second state, third state, fourth state, we could have started in the first state, gone up to the third, and then gone down to the second, or we could have, say, started at the third, gone down to the first, and then maybe gone back up to the second. So in the end, the path we took didn't really matter. In the end, we ended up, in both cases, at that second energy level. So with these compatible operators, omega and lambda, we get the same result of the same probability of landing in the same, having the same result. We just took two different routes to get there. And so basically, I just want to keep emphasizing that this is for the compatible operators. Once we're talking about incompatible, then it's a different story, because with the incompatible variables, the commutator does not equal to 0. So then you're not going to get the same answer if you operate with p first and then x, or if you operated with x first and then p. So you're not going to necessarily end up in the same spot. So that's the main difference between the two.